sec to continue on, but this is so it's all up on the screen at one time. And in the recording, you'll be able to see it just fine. Like I said, it's essentially the same thing I wrote before. I actually did it in a separate class. So what I exactly typed might be a little different, but it's all pretty much there. Now, the recording that I did on Tuesday, I did 3 recordings. I did the one for your class, and then I did 2 for my night class, because it's a 3-hour class. I do 1 recording for the first half. We take a break. I do a second recording for the second half. Something happened to the recording that I did for you on Tuesday, which it didn't capture the video component. So if you watch the video, it's just a black screen with a little circle picture of my face in the middle, which must be exciting to listen to watch. I actually don't remember if it captured the audio also, or if it, I don't remember if it captured the audio or failed to do that also. If there was no video, no audio from what I recorded for you guys on Tuesday, then I'm not posting that because it would just be an hour and 15 minutes of nothing. And then for my night class, the first half that I recorded successfully, and it was what we did last time. It was the lymphatic system stuff. And then after the break, for them, I did what we did on Tuesday, that didn't record successfully for you. And for some reason, it didn't record successfully for them either. That didn't have a video component, but it did have an audio component. And so if you wanted to review some of what we covered on Tuesday, the one that's specifically for our class, I don't think captured correctly at all, so it's not posted. But you can listen to the audio-only version of the one from the night class because it's essentially the same thing. And this is actually what I wrote on the board for that, but of course the video component didn't capture correctly, so it's not on that video anyways. But it's here, and we'll pick up with this to move on. So that's the plan going forward. Now, as I was doing this, and I was quite aware of the time, and I wanted to wrap up the quarter after if possible, I stopped this at the 16-minute mark because it was a great place to stop. It was a little transition in what's going on. What had happened, to remind you, the first half of it was all about the Rockefeller Commission and understanding about hookworm and hygiene and how that impacted the southern farmer back in the around the turn of the century. And then it started into the story of Jasper Lawrence, who this is recorded, I think, in 2008 or something like that, who was suffering from very bad allergies, living in San Diego, which is a horrible place to live if you have allergies to begin with, because it's a tropical climate, so there's a lot of tropical plants there. And then also he was a landscaper, so he was spending a lot of time around pollen and dust and that sort of thing in his profession. And then his wife owned cats who were, as he said, grandfathered into the relationship. So he had all sorts of wonderful allergens in his life, and he suffered from horrible allergies. Going to visit family back in England one time, somebody mentioned offhandedly that there was this BBC documentary about immune reactions and allergies and that sort of stuff, which led him to look into the possibility of purposely getting a hookworm infestation or infection, however you want to say it, as a means to overcome the allergy. And so he went to sub-Saharan Africa, or tropical areas in Africa, where people presently live under conditions that are similar to what were described as turn of the century post-Reconstruction South. So he found the common, what do we call it, latrine, and basically walked around. And part of why I like playing this is that segment there. I love watching for reactions when the audio engineer at Radiolab really paints the picture, so to speak, of him sloshing around, and there's that lovely kind of muddy footprint sound that's going on. And he goes out and walks through a number of different latrine areas in these conditions, and he goes home, and then the next time allergy season rolls around, he discovers he no longer has allergies. Okay, so that's where we're up to here.
And I haven't had an asthma attack since I went to Mexico. I no longer have allergies. The vast majority of the benefit that I've experienced has come from hookworm.
What is the hookworm doing? Do you know? Well, so the immune system that we learn about in elementary school is all about like these attack cells that go after foreign invaders and destroy them. Right? And that's a big important part of the immune system. But if the immune system were allowed to attack and destroy things unchecked, it could kill you. And there are lots of diseases where the primary symptoms are caused by the immune system attacking the body that it's really designed to protect. Allergies and asthma are just two of these. Some of the more serious ones are like type 1 diabetes, multiple sclerosis, Crohn's disease, in which the immune system actually starts attacking the inside of the intestines. There are like 80 of these diseases. 80. And so what scientists have found in lots and lots of mouse studies, and in some human studies to this point too, is that once the hookworms get inside the gut and the immune system actually starts attacking, somehow hookworms actually stimulate these cells, which just quiet things down and tell the attack cells to stop attacking.
So these are like lullaby cells?
Exactly. What lots and lots of scientists think, Joel Weinstock,
Tufts Medical Center,
and dozens of others, is that over
thousands and thousands of years,
hookworms almost developed in tandem with the human immune system.
coevolution. Parasites living in your body, your immune system changes.
You got to a point where the hookworms could survive safely.
The worm gets a home, there's food coming down the food pipe, and in return,
The human immune system gained some kind of
some form of
positive regulatory
advantage.
so that if you had this glitch where your immune system started attacking your own body, the presence of the hookworms would keep things controlled.
So that's the gift. You do something for the worm does something for you. So then, by that logic, what we in the West, in the richer countries, have done stupidly is we have cleaned ourselves up too much, and we don't have enough wormies in us.
Yeah, this is called,
They call it the hygiene hypothesis. The hygiene hypothesis, that we're not dirty enough.
too clean.
We function like rainforests or ecosystems, and we've entirely eliminated a class of organisms that co-evolved with us and our genetic predecessors for millions of years.
Now, I don't want to leave the impression that hygiene is bad for you. People can't go back to living in filth, kids playing in sewage by the riverbank, but in improving our hygiene, we are also excluding organisms that may be important for making us well. So then what does Jasper do about all this?
He decides to start a business selling hookworm to people.
What?
You can call him up and he will literally FedEx a dose of hookworms to your door.
How?
Sorry to break in for a second. Pat,
Hi, Jad.
where does he get the hookworm from?
This is weird. Jasper gets the hookworm from himself. Could you describe how you go about getting hookworm from your stool into one of your patients?
Well, it's a very easy organism to work with. It gets up and it walks out of it. So it doesn't take an enormous amount of work to separate it from the feces. And then having done that, I repeatedly wash them in solutions of antibiotics to make sure that anything that could live on them is killed. People contact us, we'll have them complete a questionnaire, submit a recent blood test, then we'll ship them a dose and all the materials and equipment and the instructions necessary to infect themselves.
For instance, is this a safe thing to do?
Jasper, Jasper has done tons and tons of research, but he's not a doctor. Right. The treatment is not approved by the FDA.
That's what I wonder, is there any serious sort of double-blind study trying to figure out whether some safe delivery of hookworm might make sense?
Yeah, so one of the guys who was sort of a pioneer in this hookworm research is David Pritchard.
I'm Professor David Pritchard,
Immunologist and parasitologist
at the University of Nottingham, where I study parasites and the wound healing properties of maggots. So we've now got 2 safety trials under our belt, but we've yet to conduct the trials to show that therapeutic benefit results from infection with worms.
So Pritchard infected himself pretty much just to make sure that it was safe.
What we did was 10 of us in the lab took worms at different doses. We were either given 10, 25, 50 or 100 worms, and then we had to report on the symptoms. And on the back of that study, we determined that 10 worms were tolerated.
But Pritchard, when he did this proof of safety study, actually gave himself 50 hookworms.
Oh.
Which put him out of commission for a while.
Well, I felt pretty bad. I mean, pain in the gut, really. You could feel them because they are biting on your tissues.
I mean, if you have too many hookworms, they can cause things like diarrhea, and the most serious side effect, and the side effect that makes them sort of a public health enemy, is that they can give you anemia.
So if you have too many, you lose quite a bit of blood to these parasites.
Well, if you take too many hookworm, which you're not going to if you come to us, the worst thing you're going to get is anemia. But it's not like you wake up one morning and you're drained of blood. It's very slow to develop, and it's very easy to deal with.
Jasper's kind of just gone for it. It's a very sort of like cowboy move.
For the scientific community, I think they believe that I'm premature
It's not FDA approved.
in offering this to the public.
You don't know what it is. You don't know its purity. It's not safe.
But I've talked to several clients who had really severe allergies and asthma. They say they've just achieved these great results. And Jasper also says he's seen success with a few multiple sclerosis patients and several Crohn's disease patients too. Like, how many people do you think that you have infected?
It's about 85 right now.
How is business? Is it everything that?
Business is adequate, but I honestly don't know why I don't wake up in the morning with my front garden 20 deep with people with ulcerative colitis, Crohn's disease, allergies. I just don't know why I'm not completely buried.
The way he sees it, people are scared.
Well, they're the people who are coming from a point of view of what they learned in kindergarten about clean drinking water and sewers. To them, worms and parasites are so repulsive that there's nothing good to be said about them. But I can make you better. It's simple, it's cheap. I mean, for God's sake, these organisms fall out my rear end every day, 500,000 at a time. The raw material is human excrement, for God's sake. All people have to do is open their minds. Are you really that scared of a little worm?
Thanks to reporter Pat Walters.
Thanks, Pat.
And to Jasper Lawrence.
Okay. Yeah, I thought that was him. So the rest of the podcast there is just credits and thanks, which are important, but I don't want to take class time to go through them. So just in what we listened to here, some important things that it gets to. First off, it sets up a very simplistic explanation of the immune system. And this might be, sort of how it's presented to kids in elementary school. But at its core, it's not that different from sort of what our textbook is going to present about the immune system. There are these attack cells, and they go out and fight off infections. There's certainly a lot of different types of attack cells, and how they do their job is much more involved than this suggests. But that's what most people think of as what the immune system does. And last time I was talking about, the idea of police and military metaphors to describe what's going on here. And that's exactly what it is. These are the special forces that go out and kill off things that are making us sick. Something that usually gets left out or at least, what's the word I'm looking for? De-emphasized is what are called lullaby cells in the podcast. Now, these are not, by any stretch, the formal names for any of these things. We'll talk about these different types of cells as we're talking about these things. But what the podcast is getting at is that there is this balance in the immune system, that there are cells that specifically limit the effectiveness of the attack cells we think of. Because those attack cells don't necessarily say, okay, I'm just going to get rid of this pathogen and I'm done. When they're active, they're going to go after whatever's out there. And if there are not pathogens in your body, they'll go after your body, and that's autoimmune disease. So the researcher that was talking about this, he said that parasites developed in tandem with our immune system, setting up this positive regulatory advantage, which is to say, having a low-grade infection or infestation of hookworms actually activates both attack cells and lullaby cells. And that infestation causing the lullaby cells to be active keeps the attack cells in check. The hygiene hypothesis, which basically comes out of that, is that because of the very hygienic nature of human culture today, at least in developing countries like ours, we remove the possibility of having these positive regulatory advantages by keeping us from getting these kind of infestations. And therefore, lullaby cells are not as active as they're meant to be in the system naturally, so to speak. And that leaves the attack cells to go ahead and run rampant in our system. And so possibly allergies and autoimmune diseases that we see quite a bit of these days are really just the end result of us being so hygienic. And so I'll talk about the last little bit in a second, but let me finish up. That idea was something that goes beyond the podcast. I've been using this podcast to describe this stuff for quite a while. Like I said, the podcast originally was in 2008. After I listened to it when it came out, I decided I wanted to use it for my classes, so I've been playing it for a while for my classes. And one semester after playing this, one of my students came up to me after class and said, you know, I have some firsthand experience with this. She grew up in Mexico City. Her parents, she didn't actually tell me anything specifically about them, but apparently they're American and they moved down to Mexico for whatever reason. In my mind, I imagine that she's the daughter of the ambassador to Mexico or something like that, or whatever. So she grew up in Mexico City. Okay. And then when she was 19, she moved to America, to the US, to attend college. As a freshman in college, one of her dorm mates developed some rather severe allergic reaction to something, hay fever or whatever. And she was convinced that her dorm mates were playing a trick on her, saying that, Susie or whatever her name had this horrible reaction and she was all puffy and sneezing and all that. And she was convinced that it was all a ruse, that they were making fun of the foreign girl, because she'd never met anybody that had allergies. Okay. And after listening to this, she said, it's certainly because in Mexico City, hygiene is not necessarily what it is in the United States. And so maybe allergies just don't exist in that culture because they're not as hygienic. And so people are exposed to parasites that might cause problems. You've probably heard, if you go to Mexico, don't drink the water, okay? Water is not as hygienic down there as it is here. And so it's possible for people to get sick from the water. You would think that the locals would be aware of the problem with the water too, but they're probably immune to anything that's in the water. And probably many of them have low-grade infections of parasitic worms that live in the water supply. And it might be that that helps them to not have those kind of problems. So what Jasper decided to do was to go into business. Okay. Earlier in the podcast, what we listened to last time, when he first heard about the hookworm thing, he went on the internet to see if he could find a source of hookworms. He thought at least, researchers that are investigating parasitic worms have to order those worms from somewhere, so they must get them. But nobody supplies them in a formal sense. So he decided to go into business to do that, specifically to provide hookworms for people to be self-infected with, to help control things like allergies, and multiple sclerosis would be an autoimmune disease, diabetes potentially, type 1 diabetes. I think he mentions Crohn's disease. And there are a number of those sorts of diseases that are somewhat prevalent as a group in the United States these days. And so he's suggesting there might be a way to get around that. And he says in rather colorful language how easy it is for him to harvest those things from his natural source. It did make the point that it's not approved therapy by the FDA. And in some of what he was saying, I think he ended with, "What, are you scared of a little worm?" or something like that. His attitude is certainly, people need to get over it. If it's something that can help people, then it certainly should be out there and possible. It's not approved by the FDA, but there are people that are doing work on this. And again, this is back in 2008. I haven't looked recently to see if those people have gone any further, but the safety trials were described there. Oftentimes for weird little experiments like this, it's hard to go out and find volunteers to do this. So the researchers have to basically put themselves up as the subjects. So the guy that was talking about it said a dozen or so people in his lab were infected with hookworms, and they tried 10, 25, 50, or 100 worms as the initial infestation. And what they found is that 10 worms can be tolerated. There's no real symptomology from somebody who has 10 worms in their system. Now, they're going to end up having many more worms in their system eventually, because those 10 worms, once they get into the system and they make it to the intestines where they can set up house, they're going to start having little baby worms. And so it's not that they only have 10 worms in them, but it's a small starting dose and it can be tolerated. The immune system can keep that under control. The fellow that was being interviewed directly, he was in the 50 worm infestation group, and he said it was not a pleasant experience. Okay? He had a parasitic worm infection. He probably had intestinal cramping, diarrhea, et cetera, all the symptoms that you would expect from something like that. They didn't say anything specifically about the 100 worm dosage people, but I'm sure they were having it much worse. I'm sure that in doing this controlled experiment, they would not have let anybody get to the point where they developed anemia, but probably those high worm dosages would lead to that as well. In Jasper's trip through Africa, he didn't necessarily have any control over how many worms he was infected with. And he didn't, as far as I know, didn't get any data about how much of an infestation he has. He seemed to be doing pretty well, but that's not addressed in the video there. So there's some interest in looking into this, and since this was done over the past, 7 or so years since the research that was prescribed there was performed, there might be more information about the efficacy of hookworms against certain autoimmune disorders. I don't know if they've gotten to there. I haven't heard of it, and I haven't actually looked that up. I did look up one thing I was interested in after this to find out sort of what happened to Jasper after 2008. And it's kind of interesting. Somewhere around 2010, he left the country. Okay? And the reason he left the country is kind of interesting. On a Friday afternoon, somebody from the FDA said, "Hey, Jasper, can we talk on Monday morning?" And Jasper said, "Sure, no problem." Ran upstairs, started packing, and got over the border. He was in San Diego. He went into Mexico. So he was gone before the FDA showed up, because he was probably correct in expecting that on Monday it wouldn't just be them coming by to chat, but rather for him to be served with some sort of warrant or fine or something like that for dispensing non-FDA approved therapeutics. So he left the country. I think he ended up going back to England where he's originally from. The article I was reading about this in 2010 was from an a British paper, but I don't know if he necessarily went back there. So what's sort of set up here, the idea that he has this business, that he can do that, doesn't exist, excuse me, doesn't exist anymore, that I know of. He does have a website. I think it's like jasperlawrence.com or something like that. So if you're interested in finding out, or if you want to get your own hookworms, it might be possible, but I'm not condoning or suggesting that to anybody. But it is kind of interesting to think about, you know, that something like this is going on. Now, Radiolab is a great source for scientific information that's presented for public consumption, for understanding. So I never had any doubt about this story being true or an accurate representation of the science. And they certainly interview some scientists who, you know, explain that the hygiene hypothesis is a real thing, and that there are people doing research on this specific thing as it's happening. But I did want to, before I started using this in class, just run it by one of the micro teachers. So I explained all of this to Professor Machazik. He said, oh, yeah, hygiene hypothesis, that's a whole thing. So I wanted to present this because I want you to have a little bit more understanding. A lot of people are going to leave this class with just the idea that the immune system is these attack cells, because that's what everything sort of is directed at. But understand that there's more to it. And it could be that being overly hygienic might actually be detrimental to the functioning of the immune system. So I'm not saying go out there and stop washing your hands after you use the bathroom or something like that, but it's a concept to think about in terms of what we're learning in class. So continuing on here, I want to start talking about the innate immune response. Now, in the book, they actually kind of, and you can see from this title here, they kind of separate out two things, which are often collectively considered the same or part of the same thing. So the innate immune response, or innate immunity, like I described last time, is basically what you're born with, which is what innate means. And in the book here, they say barrier defenses and the innate immune response. A lot of sources will include those barrier defenses under innate immunity, but I actually can kind of see the logic of what they're getting at here. The innate immune response is an active response. So to call barrier defenses part of that active response is a little bit incongruous, I suppose, because the existence of a barrier like your skin is not an active response. It's just part of your structure. However, we could think about what's happening in the skin. There are some active things, secretions and whatnot, that help to inhibit bacterial growth on our skin and that sort of thing. So it's whether they should really be separated out or not isn't entirely clear, but I'm fine with the way this is presented here. In the picture here, it starts off with first to set up how innate and adaptive immunity cooperate. And I said that before, that the immune system is an integrated whole. We're going to break it down and look at innate and adaptive immunity separately, but you need to keep in mind that it all is actually happening together. And so here at the beginning, they set that up. I don't want to go through this now. I want to save it for the end because I want you to understand the parts. And then when we say, okay, this is how they work together, you can see where that cooperation comes from. So as far as barrier defenses is concerned, this table here is setting it up. I said this before last time. Basically what we're talking about is the skin, the mucus lining of the respiratory tract, the mucus lining of the digestive tract, the mucus lining of the reproductive tract, and the mucus lining of the urinary tract are all barrier defenses. The skin is probably pretty obvious. When you think of you think of everything that's contained within your skin. And so everything that's not you, everything outside of your skin is foreign. And so it certainly makes sense that that's a barrier to separate you from the external environment. From an immunological point of view, that's not a complete picture of you versus not you. Okay. The openings to those tracts that I just mentioned, like the oral cavity or the nasal cavity into the digestive or respiratory systems, means that, if something's outside your body here, it could get right here. Okay. So there's not really a separation between the outside world and the cavities within these mucus-lined tracts. And so as far as the immune system's concerned, the skin and those mucous membranes are the barriers. Okay. Something can be outside of your body, beyond your skin, and it's not going to have an effect on you. Okay. That same thing could potentially go inside your body as you consciously think of you, but as long as it stays within the digestive tract or something like that, it doesn't cross over that mucous membrane, then immunologically it's still outside your body. Now that inside-outside definition there is a good representation of this idea immunologically, but we also see that as far as secretions are concerned. Okay, so remember earlier in the semester we talked about the endocrine system. Those are secretions within your body, okay, as opposed to exocrine secretions. And the word exocrine in relation to endocrine means secretions outside of your body, which is very obviously any secretions across your skin, sweat and oil and that sort of thing from your skin. But it also includes a lot of secretions across mucous membranes, okay? So the pancreas is 10% endocrine in that it releases insulin and glucagon, but 90% exocrine because it secretes digestive juices into the digestive tract, okay? So as far as secretions are concerned, the lumen of the digestive tract is outside your body just as much as where the sweat goes out of your skin is outside your body. So immunologically and secretion-wise, inside, outside is not exactly what you probably think of as inside and outside your body. If you eat food and swallow it and it's in your stomach, you think of that as being in your body. Your immune system thinks of that as still being outside the body because it hasn't crossed over a mucous membrane. The table here is basically getting at, those components of barrier defenses, but it's mentioning a few specific things because it's also itemizing some of the protective aspects of that. So for instance, it has the stomach listed here. The stomach is part of the digestive tract. It's lined with the mucosal surface, but it has a very, very low pH, okay? pH in the range between 1 and 3, depending on how much food you're digesting at any particular time. Bacteria that want to infect your body want to be at a pH of about 7.35. So if you get bacteria in the food that you're eating, which you do every day, that's going to go down to your stomach, and the low pH in your stomach is going to destroy those bacteria, and they will never cause an infection. Okay. Now, there are possibilities of foodborne pathogens passing through your stomach and then ending up causing problems because those have found a way to defend themselves against the acidic contents of your stomach. But the majority of the bacteria that you deal with on a regular basis can't survive that. So you have bacteria on your hands. It's just a fact of life. So when you pick up that cheeseburger to eat it, you're getting bacteria on the cheeseburger. Okay? And you're going to ingest that bacteria. But when it gets down to your stomach, the bacteria is going to be destroyed and it won't cause any problems. If you pick up some raw hamburger or pork before you eat the cheeseburger, then there are going to be pathogens from that raw meat that you get onto the surface of your cheeseburger and you eat that, some of them will pass through the stomach successfully because they've developed their own defenses against your stomach pH, and you'll get sick. So please wash your hands after handling the hamburger before you're making the cheeseburger, because you don't want to get that kind of contamination. But there are a lot of bacteria that you deal with on a regular basis, and these kinds of defenses keep you from getting sick. Another thing that's in here, it says normal flora. Flora, it's the same word as floral, as in, getting a floral arrangement from the flower shop. But what we're talking about here in this context, flora really means the bacteria that live inside your body. Okay? And again, it's not really inside your body from a immunological standpoint, because it's in the lumen of these various tracts. But they're non-pathogenic bacteria. They aren't there to cause an infection. If they make you sick, then their environment is compromised and they're not going to survive. They would rather keep you healthy so that they can survive where they are and get a nice, reliable source of food through the food that we eat and can't digest. And so in doing that, they contribute to protecting us by helping to reduce the pathogenicity of other organisms that might get into our system. So they kind of play a role there too. And so if that inside outside, what's us and what's not us thing already sounds confusing, part of what keeps us healthy is the population of bacteria that live inside of our bodies, inside of our gut. And they suppress pathogenicity of other things that we might ingest. Now, the innate immune response, the active part of it, has a few different components. The thing about the innate response is that it's a generalized response. Any sign of some kind of infection or damage to your body is going to elicit this response. What we want to talk about here are the components of that and how they do their job and how they can help fight off infections in this generalized way. When we get to the adaptive immune response, that's the specific one. That's what we do in response to the specific thing that's gotten into our body, like the influenza virus that we've been exposed to because our contagious friend thought that it'd be nice to come visit. That's the adaptive immune system, which is going to be very specifically targeting whatever it is that's infecting us. The innate immune response is generalized. It'll react to anything. So it'll be part of fighting off that influenza virus infection, but it's not going to be sufficient to the task in the example I just gave. Okay. But we want to concentrate on this generalized stuff to begin with. That's the innate response. The first part of that are a class of white blood cells, or I shouldn't say a class, but white blood cells that are capable of doing a particular thing. There are 5 types of white blood cells, okay, which I presented when we looked at the blood. What are those 5 types of white blood cells? Anybody remember? Does anybody remember the mnemonic I gave you to remember them? It has those words in it, but somebody started to say it. Never let monkeys eat bananas. Okay. N in never is for neutrophil. Okay. Let, the L in let, is for lymphocyte. M, monkeys, is for monocyte. Eat, the E there, is for eosinophil. And then B from bananas is for basophil. I already introduced lymphocytes, and we're going to talk about them quite a bit because they're the basis of the adaptive immune response. But neutrophils and monocytes, the other two there, are largely a type of cell that we're talking about. there's some incomplete evidence that eosinophils and basophils fall into this group too. Now, this never let monkeys eat bananas mnemonic gives us all 5 of them. But the order is important also. What does the order of this list tell us additionally? Right. It's in descending order of number. Neutrophils are the most common, okay? And they represent about 65% of the white blood cells. Lymphocytes are next at about 20 to 25%. And then monocytes are next at less than 10%. A lot of sources will provide about 8%, so, which is less than 10. So right there, if we add those numbers up, 65 plus 25 plus 10 equals what? That's 100 right there, okay? Now, these are approximations, and the 20 to 25 is a range, and the 10 is, it's saying less than 10. So these 3 types don't represent 100% of the white blood cells in our system, but they represent the vast majority, probably about 97% of the cells. And so eosinophils and basophils collectively, let me see if I can do this. Nope, I'm not going to be able to do this quite the way I want to. Collectively represent about, let's call it 1 to 3%. Okay. So as far as I'm concerned, we're going to basically ignore eosinophils and basophils. They're so rare that we don't really need to get too concerned about them. Does that make sense what I did there with the little brackets? That's supposed to say collect those together. I just couldn't put the 1 to 3 in the middle between those. So we're going to basically ignore that as far as what I'm talking about here. So there may be some evidence that they do what I'm about to describe, but we don't really care. Now, we will care about them a little bit. I have something to talk about later on, actually next time for the adaptive immune system. And so we'll save that for then. But right now, what we're talking about, we really want to think about neutrophils, lymphocytes, and monocytes as being pretty much the pretty much the white blood cells in your system. Now, lymphocytes are adaptive immune cells, and they're responsible for producing things like antibodies. So they don't apply to what I'm about to describe. The neutrophils and monocytes, which make up the other 75 to 80% of the white blood cells that we're talking about, are collectively able to become what we call a phagocyte. Now, phago means to eat. It's the root of the word esophagus, okay, which is the tube that what you eat travels down. And then cyte obviously means cell. So phagocyte very roughly translates to mean eating cell. These are cells that reach out, grab onto, and ingest and destroy various things in our body. Those are phagocytes. So back to the book here real quick. So they say phagocytes, and then they say specifically macrophages and neutrophils. Okay. What were the 2 names of the cells I said a second ago? Yeah, the neutrophils and monocytes. This doesn't say monocytes and neutrophils, it says macrophages and neutrophils. Macrophages are activated monocytes. Okay. So we could just as easily say monocyte neutrophil here, but the point is that when they're phagocytic, monocytes are called macrophages, which means big eater. Okay. They're big cells that are phagocytic. Neutrophils, when they're activated, we still call them neutrophils, but they are phagocytic cells. So collectively, you'll hear these referred to as phagocytes. occasionally, and I don't have any good sort of rule for when it happens, you might hear a reference specifically to macrophages. As far as we're concerned for this course, talking about macrophages or talking about phagocytic cells or talking about neutrophils is all described in the same thing, okay? In specific locations, one type of cell is more likely to be active than another, but we're not going to get really bogged down with that here. Okay? So whether we're talking about macrophages or neutrophils, we're just talking about phagocytic cells. Okay? Now, there's a paragraph here that talks about macrophages and paragraph that talks about neutrophils, and then there's a little sentence at the bottom that talks about monocytes. And it says here that they're the circulating precursor that differentiates into a macrophage. Okay, so they're just, when they become activated, those are macrophages. Now there's a couple other things that monocytes can do, but as far as phagocytosis is concerned, they're macrophages. Okay. So here's a little table talking about that. Now, in Blackboard, I have a number of videos, whoops, wrong videos, of things. And there's this great little video. It's got no audio component to it, and it's like 20 or 30 seconds long. But it's a video of, there we go, a phagocytic cell, and it's specifically referred to as a neutrophil here, chasing a bacterium. So I want to play this for you. This is the phagocytic cell, and then this is a little bacterium, and I assume these are red blood cells, and this is happening in a petri dish or something like that. But it's really kind of interesting to see how they move and what they do. So I really kind of wish I had a little player piano and we could do like a silent movie kind of thing. But so he's chasing that guy down, and there's an advertisement. And eventually he's going to catch up with him. I'm assuming the bacteria is male, and engulf him and eat him. That's why it's called a phagocytic cell. And in doing that, it destroys the bacteria. Okay, it's not looking for a specific type of bacterium. Just anything that's gotten into your body that's not supposed to be there will attract phagocytic cells, and they'll gobble it up. Yeah.
So are those the same cells that in an autoimmune disease attack healthy?
No. Well, from what we heard earlier when they're talking about attack cells, we could say this is an attack cell in the sense that it attacks things. But the autoimmune disease thing, those attack cells are a type of lymphocyte, which we'll talk about next time. But those attack cells, the lymphocytes that we'll talk about next time, they have the ability to tell these cells what to do. So if a lymphocyte attack cell, so to speak, decides to go on a rampage and cause an autoimmune disorder, it's probably going to recruit these types of cells to help it out. Okay. So yeah, it does tie into that autoimmune kind of thing there. So what these do, they are moving around by extending bits of cell membrane forward and then dragging the rest of the cell with them. I'm going to show you another, oh shoot, I don't have it here. Another video that I just, one of my colleagues shared with me. I'm not going to show it to you now. I'm going to preview for you a little bit. And I've only actually saved the video in one of my other courses. So I'm going to move this over to our Blackboard course so we can see it. Where did it go? There we go. So that lymphocyte attack cell is called a killer T cell. And so this is a video of a killer T cell attacking actually a cancerous cell. When I move this video over to your particular Blackboard site, and you can watch it if you want to, I'm also going to put in a link here to a web page that has sort of an expanded and updated version of this video that's a little bit better even. It's just that that video isn't publicly available on YouTube, so I couldn't post that version of the video. So I put this little one in, and I'll show you the other one there. But that one's not like the silent movie we just watched. It has some voiceover and it talks about some things. And I don't want to show that now because some of what it's describing in the voiceover has to do with what we have yet to get to next lecture. Okay. But that process that I just showed you of this phagocytic cell moving and chasing down that bacterium and then ingesting it, that's what phagocytes do. They extend their cell membrane, sort of pull themselves along, and then when they get up to the bacterium or whatever it is they're trying to get, they'll reach out around it and pull it into the cell itself within a vacuole or a vesicle, whatever you want to call it, which then is mixed with digestive enzymes, and the bacterium is digested. It's destroyed. What happens to the remnants of that bacterium later on is important next time. I'll sort of come to that next time. But phagocytes do this. Okay. So whether it's a neutrophil, which is what that video is supposed to be specifically about, or a macrophage, which is an activated monocyte, doesn't matter. They work on sort of the same principle. Okay. Another type of cell that we consider part of the innate system or innate response is called a natural killer cell. Now, phagocytic cells are usually dealing with foreign invaders like a bacterium or something like that. And they can also help to clean up any sort of cellular debris that's in your tissue. So you probably haven't made this connection yet, but back when we were talking about blood, remember red blood cells have a limited lifespan. At about 120 days, they break down. And macrophages are actually what clear away the remnants of old red blood cells. Okay. Which is to say they deal with small things. Bacteria are small, cell fragments are small, or whatever other debris might be around. Natural killer cells are able to deal with bigger things. Okay. Now, in the video we just saw, the phagocyte was much bigger than its intended prey. Natural killer cells can deal with things that are the same size, so a normal body size cell, or potentially even bigger. Okay. Natural killer cells, or NK cells, actually are a type of lymphocyte. I said earlier lymphocytes are what are the basis of adaptive immunity, but this is a lymphocyte that's actually generalized. It's part of the innate response. In the boldface down here, it mentions a few chemicals that natural killer cells secrete, which will cause the destruction of a cell. So if you've been infected with the influenza virus, you have the flu, the virus has infected cells in your respiratory tract, and that's why you're having the respiratory symptoms, because of the damage to that. Natural killer cells will be part of destroying those infected cells. And they do it basically by latching onto the infected cell and pumping it full of chemicals that'll destroy it. Okay. And that's what is going on here. Now, natural killer cells can do that in a general sense and be part of the innate response, but more importantly, they're used in conjunction with the killer T cell that I mentioned a second ago, which is part of the adaptive response. And they're recruited to help fight off specific infections. So I'll come back to talking about what these chemicals are next time when we're talking about that natural response. Okay. Let's see. Now, for these cells to be active, they have to recognize something as being foreign. And the way that happens is that these cells recognize the presence of foreign material through what's referred to as pattern recognition receptors. What it is that cells that are part of our body have a specific kind of, what's the word I'm looking for? Flavor, not a great word for it, but, and things that aren't supposed to be part of our bodies, like a bacterium or virus, which isn't a cell, but it's a pathogen, have a different flavor to them. Okay? It's easiest to explain that with bacteria. Bacteria, being single-celled organisms, are usually at the mercy of their environments. Okay? There are some bacteria that are mobile, that they have flagella or whatever, that they can move around. But usually bacteria move around within their environments passively based on what the environment's doing. Okay? So if there's water flow somewhere, they'll just follow the water along. If they want to stay somewhere, they have to connect to some surface in their environment, so to speak. And so the surface of a bacterium has specialized molecules for that. They are carbohydrate structures that are attached to either the cell membrane or cell wall directly, or connected to proteins that are part of the cell wall or cell membrane. So bacteria are covered in carbohydrates. What's the more common word for carbohydrate? Carbohydrate, sugar, right? What happens if you have, let's say, a jelly bean that's basically made out of sugar and it gets wet? Sorry? True, it would start to dissolve. But as it's dissolving and getting kind of mushy, let's say you have that in your hand, what's going to happen? It's going to get all sticky, right? So these carbohydrates that are on the surface of the bacteria, because they're carbohydrates and because carbohydrates in a water solution are very sticky, meaning that they can form hydrogen bonds very easily and that sort of thing. It gives the bacteria the ability to stick in place while its environment is moving around it, okay? It helps it to anchor to its environment. But our cells don't have the same sort of thing because they have other ways of being anchored into their environment. So one of these cells, a phagocytic cell or a natural killer cell, will recognize bacteria because they're covered in these kind of carbohydrate structures that are unlike any cell in our body. Okay? That's what it means by pattern recognition. Okay? They have a pattern of molecular structures on their surface that's foreign. And so these cells immediately know that they're not our cells and will get rid of them. That's just one example. There's other aspects of pattern recognition, that sort of thing. But that's kind of an idea. That's how these cells that we're just talking about, phagocytes and natural killer cells, know what to go after, okay, because of pattern recognition changes. And like I said, natural killer cells are actually not going after bacteria necessarily, but when a cell is infected by a virus or a bacteria, it's going to start behaving differently. So its surface pattern is going to change, and that'll be obvious to natural killer cells to some degree. They can fight off that infection. Okay. Now, other things that have to do with the innate response are chemicals. So phagocytes and natural killer cells are cells that are part of the innate response. The rest of the innate response is all chemical based. A lot of these are chemicals that are dissolved into plasma or other bodily fluids, and under certain conditions, they lend to reactions that help fight off infections, okay? There are molecules called cytokines and chemokines, which are basically hormones of the immune system. And so those can be released from certain cells when there's evidence of an infection around, and that'll help coordinate the immune response to help fight things off. There are these things called early induced proteins, and the bold-faced word here is interferon, which is an example of one of these early induced proteins. There's a few different types of interferons, but the interferon that I think is a good example of what early induced proteins are for is actually a response to viral infection. So viruses are not cells. They're not organisms. They're not living. When they infect us, it's because they're using us to make more viruses. And when a virus infects a cell in your body, it injects the viral genome, either DNA or RNA, depending on the type of virus, into the cell. And all the cells in your body have a natural response to the presence of foreign nucleic acids in them. So if DNA or RNA from a virus is injected into the cell, it'll cause that cell that is now infected to start releasing an early induced protein, a type of interferon. I think it's gamma interferon. I don't remember. There's a few different types of interferons. And it starts releasing it. It's basically a hormone that signals other cells in the neighborhood that cell's been infected by a virus. And so it tells all the other cells to be ready for the potential invasion of viruses. And they will have certain ways to limit the spread of the viral infection through that tissue. Okay. That's an example of an early induced protein. Another chemical part of the innate response is what's called complement. Now, the word complement, there are two words that are both pronounced complement. One of them has an I in it and the other one doesn't. Okay. Complement with an I, C-O-M-P-L-I-M-E-N-T, is probably what you think of when you hear the word compliment. That's like, oh, you look so nice today. That's a compliment. Complement without an I, which is spelled C-O-M-P-L-E-M-E-N-T, does not mean that. What that means is going together, working together, something like that. Okay. Complement, referring to these proteins, is spelled that way. And these are proteins, I guess we could define them as proteins that work together with the immune response to help fight off certain infections. Okay. They're referred to by the capital letter C for complement and then a number for whichever protein it is within the system. So here we have C1, C2, C3, C4, C5, and then down here, this bracket shows you in this is C6, 7, 8, and 9. Okay. So there's 9 different complement proteins. The end result of complement proteins is to form a channel in the cell membrane or cell wall of a pathogen. Okay. Now, in this picture here, they have this one thing here that kind of looks like a crown. And that's showing you that there are a bunch of little proteins together making up this channel. And then the thing that channel is inserted into has a bunch of other little holes where stuff's spilling out. And those other little holes are other little channels like in this picture. Okay? So the big one is just to show you some detail about what it looks like, but it would not be that big relative to the bacterium that it's affecting. This channel thing is called the membrane attack complex, MAC. It makes a hole in the pathogen cell membrane. And so the insides of the pathogen are going to spill out. Okay? Just like if we make holes in your skin, what's inside your body is going to spill out too. Okay? And as much as that would kill you with enough holes, it's going to kill the pathogen too. Okay? Now, this little thing is made up of C9, C8, C7, C6, which come together because of C5. Okay? C5, if we move back through this, actually separates into 2 parts. So there's C5a and C5b. Here it says a fragment from C5 joins C6, 7, 8, and 9. That fragment is called C5a. Okay, C5b is released and is not part of the membrane attack complex. To get C5a, we need something that's going to cut C5 in half into those 2 fragments. And so we see in the picture the thing that's doing that cutting is this little bump. And if we follow the arrow back, that bump is C3b, which is obviously, based on what we just saw, a fragment of C3. Okay? And in fact, C3 breaks down into C3b and C3a. C3b converts C5 or breaks it in half into C5a and C5b. C5a then organizes C6, 7, 8, and 9 and other components into the membrane attack complex. Okay. That's essentially the point of complement. Okay. But we haven't seen all of the complement proteins here. Okay. From C3 on, this is what we consider the common pathway of complement. Any activation of complement is going to go from this point to this point in the picture. It's going to form a membrane attack complex, which is a hole in the pathogen, and enough of those holes will destroy the pathogen. Okay. In doing that, C3a and C5a are, say that differently. C3a and C5b are fragments that sort of leave that pathway. Nothing said about C5b here, but C3a, the part of C3 that is not part of making the membrane attack complex eventually, what it does is it attracts phagocytes to the region. Okay? It's a little signaling molecule to phagocytic cells that they need to get into the area. Okay? It's important because shortly there are going to be some pathogens that are going to be destroyed, and we need to clean up after that. We don't want to leave the corpses of the pathogens laying around because that can also cause disease. So the phagocytes are coming to help get rid of them. Okay. What's not actually mentioned here, C3a, besides attracting phagocytes, will also, and I guess more importantly, do that by activating mast cells, which then release a signal called histamine, which then causes an inflammatory response. Now, you've probably heard the term histamine before, right? Where do you usually hear, in what context do you hear reference to histamine? Sorry? Allergies, right. And what are you taking when you have an allergy? Antihistamines, okay? Antihistamines just block mast cell activity so that you don't get an inflammatory response, which is what an allergic response basically is, okay? I just mention that because what C3a does is the exact opposite of an antihistamine. It promotes histamine release, which will attract the phagocytes and will cause an inflammatory response, which is necessary to help fight off the infection. But if we go back from C3 here, there's a bit more to the story. Okay. Now, this thing here is called C3 convertase, which means it's an enzyme that converts C3 into C3a and C3b. Okay. It's made up of fragments of two other complement proteins, C2 and C4. Now, there's actually something else probably, or some variation of this that can convert C3 also. It doesn't necessarily have to come from this. And when it doesn't come from what we see in the picture here, we call that the alternative complement pathway, which is very general. What we do see here, and then we're going to follow this back to C1 in a second, is called the classical complement pathway. Okay? The classical complement pathway actually starts with C1, which is going to be activated by the presence of a specific invading pathogen. C1 will then cause C2 and C4 to break down and rearrange into the C3 convertase. That will only happen for the classical pathway, which at its root involves antibodies. Okay. Antibodies are part of the adaptive immunity, which we're going to talk about next time. So the classical pathway is actually a little bit of a problem to start talking about here because we don't know too much about antibodies yet. But it is possible for complement to be activated in an alternate fashion through the alternative pathway. So let me just finish here with complement. There's the classical pathway, which originates from an antibody and is C1 to C2, C4 to the convertase. And then there's the, alternate pathway, which is a generalized response and begins with conversion of C3. Okay. So I'm going to move off this screen. I'll come right back to it if you're trying to write this down. Don't worry. But I want to pull the picture up real quick. So what I'm saying is this entire picture here is originating with the classical pathway, which involves antibodies, and we need to talk about antibodies more next time to entirely understand what's going on there. And that involves C1, C2, and C4. There's an alternate pathway that originates with something breaking or converting C3 into C3A and C3B. That's called the alternative pathway. Okay. So basically, if we look right here where the convertase is coming in, there's an alternate way of getting complement to get down to the membrane attack complex part down here. That's what I'm talking about here. So last little bit here is just separating out that complement has a couple of different pathways. Now, there's one more aspect to the innate response that I want to describe in some detail, and I certainly don't have time to do that in the next minute. But what it is it's the inflammatory response, which I just talked about a second ago with mast cells and histamine. So next time I'm going to start by talking about the inflammatory response to sort of wrap up the innate response stuff. And then the rest next time is going to be talking about the adaptive immunity, which is going to be kind of a rapid fire presentation because we really need more than a class time to do that. But I'm going to try to get it all done in the next class. So that's all I wanted to have today. Have a nice day.